My name is Soumya Ghosh, and today I'll be talking about approximate cross-validation methods for structured models. This is joint work with co-first author Will Stephenson, Nguyen, Deshpande, and Tamara Broderick. Using cross-validation for time series, spatiotemporal models, and other models with complex dependency structures can be very computationally expensive. Our work shows how to massively speed cross-validation up in these settings through highly accurate approximation. Many Bayesian analyses need to model structure arising from temporal, spatial, or other dependencies in the data. For example, one might be interested in analyzing traffic flow over a period of time, or in discovering activities from motion capture data, or indeed in analyzing crime statistics in a particular area of a city. All of these problems require models that carefully capture the correlation structure in the data. The resulting models tend to be complex and computationally intensive to fit. How do we assess whether these complex models work well for a particular analysis at hand? Well, cross-validation is a widely used and a simple-to-use gold standard for such model assessment. However, cross-validation requires multiple refits of the model to the data. This can be prohibitively expensive for large datasets, for structured models, and especially so for structured models fit to large datasets. Recent advances in approximate cross-validation address the computational challenge posed by exact cross-validation. But these approaches make assumptions that are typically violated in structured analysis. First, they assume data across CV folds are independent of one another. However, for most structured analysis of interest, one typically wants data across CV folds to be dependent. Second, they assume that the model can be fit at least once to the entire dataset exactly. This is often infeasible in practice where models are fit to large datasets using stochastic approximations. Our contribution lies in resolving both of these difficulties. We extend ACV through new methods, ACV being approximate cross-validation procedures, through new methods that are applicable to structured models, and through new theory which shows that the error in the approximation grows smoothly with the noise in the initial model fit. Latent variable models are a particularly popular class for analyzing structured data, and will be our focus in this talk. We arrive at these models by combining a likelihood model with priors over latent variables and model parameters. Popular examples include Markov random fields, hidden Markov models, and linear dynamical systems. Model assessments in such models is typically done via a variant of cross-validation, sometimes called structured cross-validation. Here, data for the held-out folds are drawn from within the time series or spatial extent of the original data. For example, in the case of an HMM, one might drop out parts of the time series and refit the model to assess the variability in model parameters. However, structured CV, much like original CV, requires multiple refits to the data. When even a single model fit is too expensive in practice, multiple model refits are often prohibitively expensive. One might think of using existing ACV methods to address this challenge. But as previously discussed, existing ACV approaches do not apply to this setting. For one, by construction, folds in structured CV are not independent of one another. And moreover, a single exact model fit is typically infeasible to achieve. Our contribution lies in developing a structured ACV method for dealing with the first issue and improving results, with more details in the paper, that show that the error in the approximation stemming from an inexact initial model fit is bounded. Our structured ACV algorithm is based on the key observation that learning in structured latent variable models typically involve marginalization over the latent variables, followed by maximization of the likelihood or posterior probability with respect to the model parameters. Building on recent advances in infinitesimal jackknife-based approximate cross-validation procedures, we introduce a weighted marginalization procedure. Our procedure introduces a set of weights, setting all of which to 1 recovers the original marginalization problem, while setting a subset of these weights to 0 recovers marginalization problems needed for fits across different CV folds. We carefully design new weighting schemes that, in contrast to previous work, are able to hold out data from within the structure being analyzed, thus making them applicable to structured cross-validation. Moreover, we provide weighting schemes that allow holding out both the data and the corresponding latent variable. For instance, in the case of an HMM, one might consider holding out both the data and the latent variable capturing the state assignment at a particular time instance. Together, our weighting schemes allow us to mimic the variety of structured cross-validation approaches used by practitioners in the real world. More details about the weighting schemes necessary for different models of interest can be found in our paper. We also note that marginalizing over structured latent variables can pose computational challenges. In particular, naive marginalization procedures can require exponential computation. Crucially, our weighted marginalization procedure is able to exploit efficient dynamic programming algorithms when they exist for the original marginalization problem. For example, we are able to define weighted versions of belief propagation for HMMs and other tree-structured Markov random fields. This ensures that our weighted marginalization procedure is no more expensive than the original marginalization procedure and is crucial in applying these methods to large structured models. With the weighted marginalization procedure in hand, our approximate cross-validation scheme proceeds similarly to approximate cross-validation schemes that have been proposed in the literature before. We begin by setting all the weights to 1 and fitting the model to the entire dataset. This is the initial model fit and needs to be done exactly once in our procedure. The resulting parameter is denoted theta subscript 1 in the algorithm shown here. We then perform a first-order Taylor series expansion about the weight vector of all ones. Finally, to approximate the parameters of the model, fit to data after having held out a particular CV fold, we simply set the appropriate coordinates of the weight vector to 0 and evaluate the Taylor expansion at the resulting weight vector. Each new fold no longer requires a new model fit, but just an evaluation of this Taylor expansion at an appropriately designed weight vector. The computationally expensive bits of the expansion need to be computed only once and can be reused across the CV folds. This leads to significant computational speedups and is in line with what has been observed previously when people have used approximate cross-validation procedures for unstructured CV. We do note that similar to previous work, our approximation does require the model to be twice differentiable and for the Hessian matrix to be invertible. We have found that both of these conditions to hold for a wide variety of models in practice. Moreover, modern auto-differentiation tools make the Hessian computation straightforward. Finally, a novel contribution of this work is to prove that under mild conditions, the quality of the IJ approximation decays smoothly with the error in the initial model fit. This proof is independent of the structured ACV model, ACV method that we have just described, and applies both to structured ACV and unstructured ACV that has been previously developed by other groups. This result is particularly important because it opens up the use of IJ-based ACV in situations where one needs to resort to stochastic optimization procedures for obtaining the initial model fit. Essentially, all of modern machine learning falls in this category. More details about the theorem and the empirical verification of its claims are in the paper. We now demonstrate our structured ACV method on two analyses from the literature. Additional experiments are available in the paper. We first look at anomalous traffic pattern discovery task due to Eiler et al. The author analyzed vehicular count data collected from a freeway in Los Angeles using a hidden Markov model. We reproduce their analysis using a cut of the data with 10,000 observations. We compare approximate cross-validation to exact cross-validation by comparing the loss achieved by either method on held-out folds. In all our experiments, the loss is the negative log probability of the held-out data. We consider two cases for creating the held-out folds. In the top, we show results from holding out data sampled uniformly at random from the time series. This is the IID point removal case. In the bottom, we show results from holding out contiguous blocks of the time series. This is the contiguous point removal case highlighted in the figure. In these plots, each red dot corresponds to one held out fold. The dot's x-coordinate is the loss on that fold under exact CV, and its y-coordinate is the loss under approximate CV. The closer the red dot is to the diagonal, highlighted by the dashed black line, the better the agreement between exact and approximate CV. We experimented with dropping different amounts of data. In particular, we looked at dropping 2, 5, and 10% of the time series. As can be seen from the plots, structured ACV remains an accurate approximation to exact CV across all of these settings, even when substantial amounts of the data are held out. Finally, in the rightmost figure, we plot running time of ACV and exact CV in hours as a function of sequence length. We see that the structured ACV is many orders of magnitude faster than standard CV. Observe the log scale on the y-axis. The computational benefits only grow with increasing sequence length, and our paper includes a big O analysis which guarantees this to be the case. Next, we illustrate the structured ACV procedure on an Ising model fit to reported crime statistics data from 384 census tracts around the city of Philadelphia. For the Ising model, we perform a leave one site out cross-validation analysis and compare exact CV to our approximation across different settings of the Ising model's coupling parameter beta. The results for the Ising model convey a similar narrative. We see that there is strong agreement between approximate and exact CV across held-out folds. We also observe that similar to HMMs, ACV is orders of magnitude faster. Okay, to conclude, let me briefly summarize our contributions. We extended approximate cross-validation methods to models with dependency structure. We showed that ACV can be used with noisy approximations to the initial model fit. We empirically verified this robustness to experiments that unfortunately I did not get a chance to talk about in this talk, but are available in the paper. We believe that this is an important result because it allows us to use ACV with modern machine learning techniques. Finally, we checked that the methods work in practice across diverse real-world datasets, providing fast and accurate approximations to CV. We do note that the quality of the structured IJ approximation deteriorates with increasing number of parameters in the model. This has also been observed for other IJ-based ACV methods. Developing accurate ACV methods for high-dimensional structured models is an interesting avenue for future work. Finally, for further details about our experiments, proofs, and weighting schemes, please check out the NeurIPS paper available at the archive link provided here. We also have code available for you to try out. It's on GitHub, available at this particular link shown here. With that, I conclude. Thank you.